Polymer degradation is a change in the properties tensile strength, color, shape, etc. of a polymer or polymer-based product under the influence of one or more environmental factors such as heat, light or chemicals such as acids, alkalis and some salts. These changes are usually undesirable, such as cracking and chemical disintegration of products or, more rarely, desirable, as in biodegradation, or deliberately lowering the molecular weight of a polymer for recycling. The changes in properties are often termed aging. In a finished product, such a change is to be prevented or delayed. Degradation can be useful for recycling, reusing the polymer waste to prevent or reduce environmental pollution. Degradation can also be induced deliberately to assist structure determination. Polymeric molecules are very large, and their unique and useful properties are mainly a result of their size. Any loss in chain length lowers tensile strength and is a primary cause of premature cracking. Commodity polymers. Today there are primarily 7 commodity polymers in use: polyethylene, polypropylene, polyvinyl chloride, polyethylene terephthalate, polystyrene, polycarbonate, and polymethyl methacrylate. These make up nearly 98% of all polymers and plastics encountered in daily life. Each of these polymers has its own characteristic modes of degradation and resistances to heat, light and chemicals. Polyethylene, polypropylene, and polymethyl methacrylate are sensitive to oxidation and UV radiation, while PVC may discolor at high temperatures due to loss of hydrogen chloride gas, and become very brittle. PET is sensitive to hydrolysis and attack by strong acids, while polycarbonate depolymerizes rapidly when exposed to strong alkalis. For example, polyethylene usually degrades by random scission, that is by a random breakage of the linkages that hold the atoms of the polymer together. When this polymer is heated above 450 Celsius, it becomes a complex mixture of molecules of various sizes that resemble gasoline. Other polymers like polyalpha-methylstyrene undergo specific chain scission with breakage occurring only at the ends. They literally unzip or depolymerize to become the constituent monomers. Photo-induced degradation. Most polymers can be degraded by photolysis to give lower molecular weight molecules. Electromagnetic waves with the energy of visible light or higher, such as ultraviolet light, X-rays and gamma rays are usually involved in such reactions. Thermal degradation. Chain growth polymers like polymethyl methacrylate can be degraded by the molasses at high temperatures to give monomers, oils, gases and water. The degradation takes place by chemical degradation. Sylvolysis step growth polymers like polyesters, polyamides and polycarbonates can be degraded by sylvolysis and mainly hydrolysis to give lower molecular weight molecules. The hydrolysis takes place in the presence of water containing an acid or a base as catalyst. Polyamide is sensitive to degradation by acids, and polyamide moldings will crack when attacked by strong acids. For example, the fracture surface of a fuel connector showed the progressive growth of the crack from acid attack to the final cusp of polymer. The problem is known as stress corrosion cracking, and in this case was caused by hydrolysis of the polymer. It was the reverse reaction of the synthesis of the polymer. Ozonolysis. Cracks can be formed in many different elastomers by ozone attack. Tiny traces of the gas in the air will attack double bonds in rubber chains, with natural rubber, polybutadiene, styrene butadiene rubber and NBR being most sensitive to degradation. Ozone cracks form in products under tension, but the critical strain is very small. The cracks are always oriented at right angles to the strain axis, so will form around the circumference in a rubber tube bent over. Such cracks are dangerous when they occur in fuel pipes because the cracks will grow from the outside exposed surfaces into the bore of the pipe, and fuel leakage and fire may follow. The problem of ozone cracking can be prevented by adding anti-ozonants to the rubber before vulcanization. Ozone cracks were commonly seen in automobile tire sidewalls, but are now seen rarely thanks to these additives. On the other hand, the problem does recur in unprotected products such as rubber tubing and seals. Oxidation. The polymers are susceptible to attack by atmospheric oxygen, especially at elevated temperatures encountered during processing to shape. Many process methods such as extrusion and injection molding involve pumping molten polymer into tools, and the high temperatures needed for melting may result in oxidation unless precautions are taken. For example, a forearm crutch suddenly snapped and the user was severely injured in the resulting fall. The crutch had fractured across a polypropylene insert within the aluminium tube of the device, and infrared spectroscopy of the material showed that it had oxidized, possible as a result of poor molding. Oxidation is usually relatively easy to detect owing to the strong absorption by the carbonyl group in the spectrum of polyolefins. Polypropylene has a relatively simple spectrum with few peaks at the carbonyl position. Oxidation tends to start at tertiary carbon atoms because the free radicals formed here are more stable and longer lasting, making them more susceptible to attack by oxygen. The carbonyl group can be further oxidized to break the chain. This weakens the material by lowering its molecular weight, and cracks start to grow in the regions affected. Galvanic action Polymer degradation by galvanic action was first described in the technical literature in 1990. This was the discovery that plastics can corrode, that is, polymer degradation may occur through galvanic action similar to that of metals under certain conditions and has been referred to as the Fordry effect. In the aerospace field, this finding has largely contributed to aircraft safety, mainly those aircraft that use CFRP, and has resulted in a wide body of follow-up research and patents. Normally, when two dissimilar metals such as copper and iron are put into contact and then immersed in salt water, the iron will undergo corrosion, or rust. This is called a galvanic circuit where the copper is the noble metal and the iron is the active metal, that is, the copper is the cathode or positive electrode and the iron is the anode, or negative electrode. A battery is formed. It follows that plastics are made stronger by impregnating them with thin carbon fibers only a few micrometers in diameter known as carbon fiber reinforced polymers. This is to produce materials that are high strength and resistant to high temperatures. The carbon fibers act as a noble metal similar to gold or platinum. When put into contact with a more active metal, for example with aluminum in salt water, the aluminum corrodes. However, in early 1990, it was reported that amide-linked resins in CFRP composites degrade when bare composite is coupled with an active metal in salt water environments. This is because corrosion not only occurs at the aluminum anode, but also at the carbon fiber cathode in the form of a very strong base with a pH of about 13. This strong base reacts with the polymer chain structure, degrading the polymer. Polymers affected include bismuthamides, condensation polyamides, triazines, and blends thereof. Degradation occurs in the form of dissolved resin in loose fibers. The hydroxyl ions generated at the graphite cathode attack the OCN bond in the polyamide structure. Standard corrosion protection procedures were found to prevent polymer degradation under most conditions. Chlorine-induced cracking . Another highly reactive gas is chlorine, which will attack susceptible polymers such as acetyl resin and polybutylene pipework. There have been many examples of such pipes and acetyl fittings failing in properties in the US as a result of chlorine-induced cracking. In essence, the gas attacks sensitive parts of the chain molecules, oxidizing the chains and ultimately causing chain cleavage. The root cause is traces of chlorine in the water supply, added for its antibacterial action, attack occurring even at parts per million traces of the dissolved gas. The chlorine attacks weak parts of a product, and in the case of an acetyl resin junction in a water supply system, it is the thread roots that were attacked first, causing a brittle crack to grow. Discoloration on the fracture surface was caused by deposition of carbonates from the hard water supply, so the joint had been in a critical state for many months. The problems in the US also occurred to polybutylene pipework, and led to the material being removed from that market, although it is still used elsewhere in the world. Biological degradation. Biodegradable plastics can be biologically degraded by microorganisms to give lower molecular weight molecules. To degrade properly, biodegradable polymers need to be treated like compost and not just left in a landfill site where degradation is very difficult due to the lack of oxygen and moisture. Stabilizers. Hindered light stabilizers stabilize against weathering by scavenging free radicals that are produced by photooxidation of the polymer matrix. UV absorbers stabilizes against weathering by absorbing ultraviolet light and converting it into heat. Antioxidants stabilize the polymer by terminating the chain reaction due to the absorption of UV light from sunlight. The chain reaction initiated by photooxidation leads to cessation of cross-linking of the polymers and degradation the property of polymers. See also, applied spectroscopy, forensic engineering, forensic materials engineering, forensic polymer engineering, environmental stress fracture, polymer engineering, polymer, stress corrosion cracking, environmental stress cracking, weather testing of polymers. Bibliography, Lewis, Peter Rees, Reynolds, K. and Gag, C. Forensic Materials Engineering, Case Studies, CRC Press, Rin, Mayer, Plastics Failure Guide, Cause and Prevention, Hansel SPE. Wright, David C., Environmental Stress Cracking of Plastics RAPRA, Lewis, Peter Rees, and Gag, C. Forensic Polymer Engineering, Why Polymer Products Fail in Service, Woodhead CRC Press. References, ABRV Lapshin, A.P. Alakin, A.G. Kirilenko, S. Aladintsev, V.A. Krotkov. Vacuum ultraviolet smoothing of nanometer scale asperities of methyl methacrylate, surface. Journal of Surface Investigation X-ray, Synchrotron and Neutron Techniques 4, 1 Euro 11 doi, 10.1134 per second 10274510100015. ISSN 1027-4510. Fordry, Michael C. Relationship of Graphite Polyamide Composites to Galvanic Processes. Society for the Advancement of Material and Process Engineering Journal 2, 1288 Euro 1301. ISBN 0-938994-56-5. http global.jst.gojp20090422/200902037896192534. Aviation Week and Space Technology, ATF researchers address potential for bismulamide degradation November 26, 1990, pages 122 to 123. External links, the journal Engineering Failure Analysis, Methods of Analysis, Forum on Integrated Analysis of Polymer Degradation,